Hello, today we're going to talk about Topic 1, Section 15, Eigenvalues and Eigenvectors. Okay, so this is all all this part up here is all the written textbook explanation, okay? What we want to do is we want to notice what's happening here. So if I take this matrix and I multiply it by this matrix, I'm going to get this matrix. And then if we notice something interesting about it, okay, there's a relationship between this one and this one, okay? It's 7 times the original, right? So if we notice that, we can think of this formula. If I do a matrix times some vector, some column, then that equals another value times that same vector. Okay, this doesn't happen often, but sometimes this does. The value is called the eigenvalue, and the vector is called the eigenvector. Okay, so let me show you how you can get it. So example 1. So Cognity explains it as this. So we have a matrix times your vector equals some value times your vector. So value times your vector. So then if I want to solve for one of these, I'm going to move that over. So I'm going to get this. And then what I can do is I can factor out that x. But I can't just subtract a value from a matrix. So I'm going to multiply it by the identity matrix. Okay, so that way we don't, that way we can eventually combine those and then have x. Alright, so just like with quadratics, when we factor, alright, we can set each part equal to 0. Okay, so obviously we can't have a vector equal 0. That doesn't make sense. Okay, so we focus on this part. So a matrix minus a value times the identity matrix. Alright, when that doesn't equal 0, alright, again, that's when you're focusing on the x, the vector, making it 0. That's not an interesting solution. Alright, so we're not going to focus on that. This, solving it when it does equal 0, is going to let us solve. Okay, so I'm going to take this matrix and I'm going to subtract some value, right, times the identity matrix. So remember, that's the diagonals are just 1. So I'm going to have 3, 5, 3, 1 minus, I'm going to distribute that lambda, or that value. And then, alright, I can combine those. So I get 3 minus lambda, 5, 3, 1 minus lambda. Okay, and then we're solving for this part being 0, so we're looking for the determinant of this. So the determinant of this must equal 0. So we do 3 minus the value times 1 minus the value minus 15. Oh, and my pen. There we go. So we want to make that happen so we can solve that. So I believe it comes down to lambda squared minus 4 lambda minus 12 equals 0. So here we can get the value to either equal -2 or 6. So we have 2 eigenvalues, -2 and 6. Okay, So let's do another one. So we're going to just focus on 2 by 2 matrices. So when we do 2 by 2 matrices, all right, the shortcut is we're just taking 3, the left diagonal, we're subtracting a value, right? That was our shortcut. And then find the determinant of that has to be 0. That's how we find the eigenvalues. So 3 minus a value times -1 minus a value minus -8 must equal 0. So we FOIL and simplify. You should get lambda squared minus 2 lambda plus 5 equals 0. So here we actually solve, and we can use the quadratic formula, and we get something gross. We get 2 lambdas, we get 1 plus or minus 2i, right? We get something imaginary. Okay, so just like any quadratic, we can get 2 real eigenvalues, 1 repeated, so like a double root, or 2 complex eigenvalues. Okay, so those are your possibilities. Okay, so now let's find the matching eigenvectors. Okay, so let's go back to, this is example 1. I know it says example 3, but it's repeating this one, right? We did this one back there. So, so if we think about what we did back there, okay, we got 2 eigenvalues, -2 and 6, and we had this. Okay, so we had this matrix minus lambda times the identity matrix times our vector, remember x was our vector, had to equal 0. Okay, so this will help explain, well, see how this ends up being exactly what we need. So, again, we found our values to be -2 and 6, and we know alpha minus lambda times the identity matrix times our vector must equal 0. So our matrix 3, 5, 3, 1 minus, well, we'll use one of our values, so we'll start with -2 times our identity matrix. All right, and then all of that times our vector matrix must equal 0. All right, so we simplify this part. Okay, so we should have 5, 3, 3 when you work out these matrices. And then we need a vector, so remember it's a column matrix, so I'm going to call that A and B, and that has to get me 0. So that would be giving you a 2 by 1, 2 rows by 1 column. So we multiply these two together, so we get 5A plus 5B, and multiply this row times that column, and then those have to equal 0. So now we just have a system, and we can just combine those. So notice that both of these can be converted to A plus B equals 0, right? So they're the same form, so we know A is just equal to -B. Now, remember here, you're trying to find the relationship of a vector, and this vector really could be a whole slew of things, you know, based on multiples. So just think, you have A represents -B, so our vector matrix, or I guess our eigenvector, should be AB, right? That's what we identified it as up here. So A represents negative B. So we replace that A with negative B, and then notice this is just negative 1, 1. So we can use this as our eigenvector, right? We just divided by B. Kind of think of it like that. Okay, so the eigenvector for negative 2, right, for the eigenvalue negative 2 would be negative 1, 1. Okay, so let me show you what I mean for 6. So we can do the same thing. So we have our original matrix, 3, 5, 3, 1. We're going to subtract 6 times the identity matrix, and then multiply that by our eigenvalue, or eigenvector, and get 0. So on this one, let's see, you should end up with negative 3, 5, 3, negative 5. So you end up with negative 3a plus 5b and 3a minus 5b. Again, those both equal 0 because they have to equal that 0 matrix. And so here you find a relationship between a and b. You notice they have the same relationship. They can both these equations can simplify to get your a by itself. So a is just 5/3 b. So we think about our vector, and if we replace it, we have 5/3 b and b. That's kind of gross, okay? So what I like to think about is you can pull that b out, but then I'm also going to multiply it by my numerator. My denominator, so I can get rid of that. So I'm going to get 5b and 3b. So this can turn into 5, 3. So these are your eigenvectors. Okay? Okay, so I'm going to show you how to do this through your calculator. So you go to your matrix, which is second x to the negative 1, the inverse of x. Go to Edit. I'm going to change the first one to a 2 by 2. And let's see, enter 3, 5, 3, 1. And then I'm going to quit. So first let's just check our eigenvalues are correct. So I'm going to plot them. So I can do this through y equals. And I'm going to take our matrix, so second x inverse. I'm going to select matrix A. And then I'm going to subtract x times the identity matrix. So second matrix. And then we go to math. Then you hit number 5, which is identity. And we want a 2 by 2, so we just hit 2. And then we hit graph. Uh-oh, I hit something incorrectly. What did I do? Let me see. Oh, silly me. I forgot to put, we are doing the determinant of this. Remember, that's how we found our eigenvalues for this one. We found, we multiplied by x times the identity matrix and then took the determinant. So I need to insert that. So second, delete, then do second matrix, go to math and hit DET, which stands for determinant. There we go. Now I can graph it. What am I doing? Go to it, determinant of A minus x. Oh, and it's not done. Okay. I need to close my parentheses. Okay, I'm just being silly. I had my stat plot on from when I did statistics the other day. So I had to go to second y equals and turn off my plot. So then I hit zoom 6 to do zoom standard, and then now my graph should pop up. There we go. Okay, so here we can check that our eigenvalues are correct, because notice that the x-intercepts are at -2 and 6. So we found our eigenvalues. That's the math way to do it. Okay? And then if I wanted to figure out my eigenvectors, there's a whole bunch of ways on the internet to do it kind of in a technical form, and I don't know, maybe it'll make sense to you. It didn't really make sense to me. So what I would do is I could just do this math portion through my calculator if you wanted. Second matrix, take that, then subtract your eigenvalue times your identity matrix. So we go to math, then we go to 5, and it's a 2 by 2. So then there, it easily found my matrix, but again, it wasn't that hard to do it by hand either. And then take it from there. So that's how you can utilize your calculator. So here, we're going to talk about how to raise a matrix to a power. All right, so really matrix multiplication can get very complicated. Even just saying it is difficult. So here, what we're going to focus on is a 2 by 2 and a diagonal matrix, just so we can get the gist of it. Oh, okay. I accidentally left off one of the examples. Here, let me go back and put it here. So example 1 was an example where it started off, let A equal this matrix, and you're given your two eigenvectors, and then you're showing this relationship. All right, that's all that example 1 was, showing this relationship, where A is your matrix, so your 1, 2, 3, 0. P represents your matrix that has your two eigenvectors. So this would be like eigenvector 1, and this would be your eigenvector 2. And that's going to be the same as taking that, you're still your eigenvectors. Sorry, let me write it all out. And then multiplying it by the diagonal, all right, matrix with your eigenvalues. Okay? So that's what you're showing. That's what this was showing. Okay, that relationship that we already know. But now you're just combining all of them. Instead of just getting one value in one vector, you can get all of them. All right? So let's apply it here. So this one is showing this relationship. Okay? So from the first example, we realized that AP equals PD. And then to move P to the other side, we could multiply by the inverse property. And when you multiply a matrix by its inverse, you get the identity matrix. And whenever you multiply by the identity matrix, you get just the other matrix, right? Nothing changed. It's like multiplying by 1. So that's how we proved, all right, and that's how we show that that's true for this matrix. Okay? So now what we want to do is we want to apply this idea and find a to the 5th. Okay, so a to the 5th is going to represent p to the -1, or the inverse of p to the 5th. So if we multiply this out, that's one of them, times it again, times it again. Yep, I'm going to keep doing it. I've only got 3 of them. Yep. Gonna show every single one. Okay, so we get all 5 of them. Oh, then notice what happens. Whenever you multiply a matrix times its inverse, you end up with the identity matrix. Correct? So we can write this as PD identity matrix, D identity matrix, D identity matrix. Oh, I'm going to lose count here. 1, 2, 3, 4, DP. So multiplying by the identity matrix does really nothing. So then you get P, D times D times D times D times D times P, the inverse of P. Oh, and then look at that. Look at how beautiful this is. So all I needed to do is it breaks down into this nice little format. Okay, so now I'll actually find out what a to the 5th is. All right, we should go and figure this stuff out. So we need the eigenvalues and eigenvectors. So you find your eigenvalues to be 2 options, -4 and 8. So let that be the first one. Let this be 8 be my second one. So then the vector for -4 should be 2, 1. And the vector for the second lambda should be, let's see, 2, -1. If you need help, just ask me in class and I'll be happy to go through those again. But again, you can use your calculator, same process as before. Find those and then write out each of these. Remember, P represented the matrix of your vectors. So let's do our first lambda first. So 2, 1, and then 2, -1. All right, D is going to represent the diagonal matrix of your lambdas. And our lambdas are -4 and 8. And the inverse of P is just 1 over the determinant, and then you flip them and change the signs, right? We can do the inverse. You can also use your calculator. You should get 1/4. Oh, I put that in the wrong. I said that weird. That's what I meant to say. So that's the inverse of P. Okay, so now we can plug those in there. I know, a lot of steps. So, we're just going to go up here because I want to leave it all on one page. Sorry, I know it's all over the place. So then P, so is 2, 2, 1, -1. Our diagonal matrix is that -4, 0, 0, 8. We're going to raise that one to the 5th and then multiply by the inverse matrix. And -1/2. Okay, so we multiply that out. Oh, and what's nice is that this, you literally just raise those to the 5th. So that's just this part. Ooh, it's not working. This part is literally -4 to the 5th, 0, 0, 8 to the 5th. Okay, so you just bring that one down, you bring that one down, multiply them out. I would use a calculator personally, so I don't do anything wrong by hand. And I would get 15,872. Let's see, -33792, -8448, and 15,872. Okay, so that's how we can write out a matrix to an exponent, right? We can use eigenvalues and vectors. And of course, what's great about knowing this is that your exam is going to have that formula on there, okay? You just have to realize that n could be anything, right? So if we want to raise it to the fifth, or if we just want to know what the matrix is, right, if we're just asking for the values and vectors, then n would be 1. Okay, so keep that in mind. You are going to get that formula. Oop, too far. Okay, so that's all you pretty much need to know about eigenvalues and vectors. I'm available in class when you need me.